Well, happy International Moon Day to everybody. I was hoping to be in Boulder with my colleague Melissa Badler. Unfortunately, we couldn't make it. I'm actually now on the moon in our company mission control in Ottawa, Canada. It's our lunar analog test bed with our test rover platform. I'm hoping by the end of the talk to give a short glimpse into our operation software. But first, I'll just go through some slides. I'll first introduce some of our technology for enabling kind of a level of science autonomy for rover-based missions, and talk about an upcoming mission contribution that's flying to the moon this year, and then some experimental results at a very high level from our field testing in Iceland for a Mars 2020 research project. So to begin with, as you all know, I think there's a common set of challenges for rover-based science missions on the moon that require a good understanding of the environment and the lunar surface around the rover as it moves along, for hazard assessment, for navigation, for building a map that supports navigation, but also geologic context mapping and geotagging data products from multiple instruments, and then also for identifying the right targeting sequences for capturing data from a variety of instruments and prioritizing data for downlink. So to address these challenges, we've developed over the last few years a imaging autonomy system for, well, we started out with the Mars context, and we then advanced this into a lunar surface context, where we use a deep learning technology to identify each pixel in an image, which can be from a rover navigation camera, from a context camera, into a predefined terrain class that is of interest to the science team. So this is a kind of a baseline data product you can imagine could be useful for advancing other data products. Our classification scheme here is simply things like crater rim, crater floor, and using kind of a relative pre-configured scale, boulder and pebble as well. And also the wall in our case, because we collected images in our indoor facility, which can be replaced with sky in a real mission. The intention for these data products could then be to use them on board for any autonomy required on board the rover, or it can also then be used in a variety of ground-based operations use cases. So I just wanted to quickly highlight a couple use cases on board that we've been thinking and conceiving of and having discussions with many people. The first is autonomous targeting. So let's say you have a thermal infrared imager or a multispectral imager or LIBS, and you have kind of a preconceived notion of the different targets you want to target and collect data for. So this technology allows you to identify the surrounding environment, identify features, and then rank them for collecting data from specific instruments. So this is an area where we're interested in doing some R&D in the near future. Happy to talk more about it with anyone. Another use case is downlink privatization. So very similar to the strategies used by NASA for Mars rovers over the years, where you capture images, identify and rank features, and prioritize a certain set of them for immediate downlink, whereas the rest can be downlinked at another time. So that just helps the science team on Earth make sure they get the right data at the right time to maximize their return. And if you have pre-annotated images using this technology, that can save a lot of time for ground-based analysis. So if you have it built into a particular user console, you can share objects across with other users. You can do some cool things like intelligent feature query, where if you have a catalog of objects of rocks and craters of different types, you can use natural language processing and things like that to quickly retrieve a set of features. And then, of course, you can add other measurements, data products, integrate that into geographical information systems for wider analysis. I just wanted to quickly highlight, so the technology I've described, we're planning to demonstrate that on the surface of the moon early next year. So this is launching on the iSpace mission M1 towards the end of the year. I think everything's on track. And along with our AI demo on the lander, that lander will also be deploying a rover from the Mohammed bin Rashid Space Center in the United Arab Emirates. So we are collaborating with MBRSC to use their rover images in order to demonstrate our AI capability for extracting key features. So in this capability demonstration architecture, the AI processing will be done on board the lander on the surface of the moon. We're hoping or anticipating that this is going to be the first demonstration of deep learning on the surface of the moon. And then the data products will be downlinked to Earth. In a future scenario, of course, we may be able to help use that on board. A couple slides on Sandy. So this was featured in our abstract. I think my colleague Melissa could speak more about this. So this was a P-STAR funded project we deployed with a variety of academic partners led by Ryan Ewing at Texas A&M University in 2019 and 2021 to emulate March 2020 rover operations. And the objectives of this P-STAR project was twofold. One, how would autonomous terrain characterization, such as what I've described earlier, improve scientific decision-making as well as return of scientific objectives? And two, similarly, how would using a drone, so mimicking Ingenuity, help with operations workflows as well? And so we've completed both seasons of deployment in the field, collected data, and have begun assessing the data for the types of metrics we were looking for. I've just put a quick summary here. I invite anyone who's more interested to speak with us more, especially Melissa and other colleagues in the team. So we had 6 scenarios to run in 3 landing sites. One with human input and no terrain classifier, so it's kind of a standard model. One where you did include the terrain classifier, so the science team had access to the automated terrain classifier product in their analysis. One with the terrain classifier, but with some level of autonomy to enable like a walkabout scenario. And then 2 scenarios with the drone and 1 control. So we got some interesting results about science return and decision-making efficiency. I think it was no surprise that, of course, the control team, where field geologists went into the field, had the highest science return. But it was interesting to see the differences here between how the science return and decision-making efficiency is affected. So those are my slides. I'll quickly hop over to another tab just to give a quick glimpse into our user operations interface for, I think, maybe 1 minute is all I have here. So this is an interface we've developed over the last few years, designed for rover operators as well as payload and science teams to interact with the scene where the rover is operating. We have a basic on-screen drive controller for rover drivers. Cool set of features we've included here is visual overlays, so distance markers, a grid, and wheel tracks to show where the rover goes, kind of a hazard overlay. All of this is based on a stereo camera that's running on board. We also have a pan tilt zoom camera running on board, so if you want to get close up to a particular rock or crater or any other feature, I can just quickly turn around, and it's kind of where our light source is. We also have a map where data is aggregated as the rover is driving along in real time. And then we have some capabilities here for driving autonomously. So if I want to control and click to a certain point, I can also inspect the scene and then use our autonomous path planning tool to get there. So happy to do a more elaborate description of this interface another time to anyone. We use this all the time. We just used it for a few educational rover activities to celebrate Moon Day today. So I think I'm at the 10-minute mark, so I'll stop there.